Again, this is a really famous limit, and you're going to see this limit again in the last chapter. I believe it's chapter 9. It's a very famous limit. The question is, how do we find this limit as x goes to infinity? The first thing we should always try to do is what is happening. What value do we get, like infinity over infinity or 0 over 0? What is happening here as x goes to infinity? First, look at the inner portion. What is happening to the inner portion? We have 1 plus, okay, where does 1 over infinity approach? 0, right? 1 over infinity goes to 0. And on the power you have infinity. So what we have is we have something of the form 1 to the infinity. Now the thing that we have to be careful about is to recognize this is not exactly 1 to the infinity, but what it really is, the bottom is approaching to 1, and the top is approaching to infinity. Because if you had exactly 1 to the power of infinity, what would the answer be in that case? If you have exact constant of 1 to the power of infinity, that would be exactly 1, right? The 1 times any number of itself is going to be 1. But the key here is the bottom is not 1. The bottom is approaching to 1, because the bottom is technically 1 plus 1 over x. That 1 over x part is going to 0, so the bottom is approaching to 1. The top is approaching to infinity. So the question is, again, two powers are at play here. Which one is going to succeed, or maybe somewhere in the middle? Now, any suggestions how I could start this problem? Any suggestions? Apply ln. Grace's suggestion is a good one. How do we know we're going to apply that technique of applying ln to both sides? By the way, your group activity, I believe question number 1 had a problem just like this one, where you have to apply the ln. How do you know you have to apply the ln function? The x power, also the x base. If you have a variable base, inside the parentheses there's a variable, right, and on the power there's a variable, then you know that this is a good approach. So let's do that. Let's y be equal to the given expression. Let y be equal to 1 plus 1 over x to the x. Then we're going to apply ln y to both sides. Ultimately, we're going to need to get rid of the ln y, but right now we're bringing in temporarily to help us with the problem. Okay, as I bring in the ln y, I'm going to also do a simplification. This can be written as x times ln of 1 plus 1 over x. Did everybody see what happened there? Basically, I applied ln to both sides. At the same time, I brought the power down. That is a property of logs. We can do that, right? Only with logarithmic functions. Okay. Now let's see what happens. If you were taking a limit as x goes to infinity, if you were taking a limit as x goes to infinity of both sides, what would you have on the right-hand side? Okay, x, just that's going to infinity, right, times ln of 1 plus 1 over x. What would that be? Ln of, as x goes to infinity, first look at the inner part, 1 plus 1 over x. Where is that going towards? One plus 1 over x is going towards 1. How about ln 1? Where does ln 1 go? To 0, right? ln 1 is 0. So now we have something of the form infinity times 0. Now we're a little bit closer to applying Lhopitals rule, because anytime you have infinity times 0, there is a way to rewrite it as either infinity over infinity or 0 over 0. You just basically flip one of the expressions and put in the denominator as follows. We can rewrite this as ln of 1 plus 1 over x divided by 1 over x. Are we still taking a limit as x goes to infinity? And on the right-hand side, limit as x goes to infinity. Okay. Why did I bother doing this? By the way, do you agree I can do this? If we go back and check our answer, if you're dividing by a fraction, you multiply by the reciprocal, right? So this is a pretty common trick that we use. If you have 0 times infinity, or infinity times 0, you try to put one of the expressions on the bottom as a fraction. So now what do we have? The top is approaching where? 0. How about the bottom? 1 over infinity? That's also going to 0. So now this is a form that we can work with. This is 0 over 0. So now we know what to do with Lhopitals rule, hopefully, right? Okay, so what does Lhopitals rule say that we can do at this point? You take the derivative of the top first, and then take the derivative of the bottom separately, right? Okay, first of all, derivative of ln of 1 plus 1 over x. What is in general derivative of ln u? 1 over u times u prime, right? From the chain rule, you do 1 over u times u prime. Okay, in this case, okay, so as x goes to infinity, first differentiate the top, and you will have 1 over 1 plus 1 over x. Now, what is the derivative of the inside? What is the derivative of 1 plus 1 over x? Derivative of 1 is 0. What is the derivative of 1 over x? Negative 1 over x squared, right? And on the bottom, differentiate the 1 over x on the bottom. What do we get there? Negative 1 over x squared on the bottom also. And luckily, those are completely going to cancel each other. So all we're left with is limit as x goes to infinity of 1 over 1 plus 1 over x. Once again, let's see what happens to this as x goes towards infinity. Any thoughts? 1 over 1 plus 0, in other words, 1 over 1, in other words, just 1. Because 1 over x goes to 0, so we're left with 1. Now remember, on the left-hand side, we have limit as x goes to infinity of ln y. Remember, we had to take ln of both sides to begin the problem. So now you don't have the answer to the original question, but you have the question, the answer to ln y. Where does ln y go to? But we really want to know, where does the original function, which we called y, goes to? If you know ln y equals to a number, can you tell me what is y? If you know ln y is equal to 1, what can you tell me about y? Remember exponentiation, you can exponentiate both sides, e to the ln cancel, so y equals e to the 1, right? So if you know the limit of ln y as x goes to infinity is 1, the answer to the original question then will be what? E to the 1 or e. So if ln y goes to 1, then the limit of the original question, which is what we called y to be, is going to be e to the 1 or e. And I'm just going to write the whole result one more time. So what we've found is as follows. Limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. This is a very important result. Later on, we're going to see this again. For example, many of you have seen that formula in college algebra or pre-calculus. Compound interest formula, A equals PERT. Remember P times e to the RT? Guess what? Somewhere in the proof of that, there is actually this proof that this limit goes to e, because this represents, like, x usually represents a number of compoundings, and as you're increasing the number of compoundings, you know, twice a year, 5 times a year, 365 times a year, infinitely many times, basically a certain formula becomes exponential, and that's where the P times e to the RT formula comes from. This limit is on the basis of the proof of that formula. Okay, so just to review what we did here, if you have a limit question where the variable is included in the base and the variable is included in the power, we're going to let y be equal to the right-hand side, take ln of both sides, but at the end, don't forget to get rid of your ln. Okay? And just to remind you, last class we did a problem similar to this one. Which one was that? Did we do x to the 1 over x? Not that one, I believe. Did we do x to the 1 over x as x goes to infinity? That was a question very much like this one, variable base, variable power. Okay? Now let's do a few examples from improper integrals. Again, we started doing that last time. Just to reiterate something we said last class, what is really an improper integral? It's an integral usually that has infinite limits. And the idea I mentioned to you was completely ignore the question, completely ignore the limits at first, do the integral as you would normally do the integral. And at the end, when you have the limits that involve infinity, just go ahead and substitute those. And if you need to use Lhopitals rule as needed. Okay, here's another example of improper integrals. Let's find the integral from 1 to infinity of dx over cube root of x minus 1. And I'll give you a few moments to think about it. Actually, let me change the limits for this question from 2 to infinity. From 2 to infinity of the given problem. Dx over cube root of x minus 1. Take a moment. So let u be x minus 1. Then du equals dx. So this is the same integral as integrating du over u to the 1/3. In other words, we need to integrate u to the negative 1/3 du. Right? Again, we learned so many complicated techniques, but this was just a simple u substitution question. So now let's just apply the power rule. So add 1 to the power, or add 3/3. So we have u to the 2/3 divided by 2/3 or times 3/2. And don't forget to bring the u back in terms of x before you look at the limits. And the limits are from 2 to infinity. So what happens is we deal with the first limit. And remember, anytime one of the limits is infinity, technically we're taking a limit as x goes to infinity, because infinity is not just a number. So what happens when you substitute the upper limit, when you take a limit as x goes to infinity of this quantity? What happens? Infinity minus 1 is still infinite, right? Infinity to any power still going to be infinity, times another positive number is still infinity. So what we're getting is infinity. Minus, now substitute a 2 in there for x. We're going to get 1 to the 2/3 times 3/2. Basically a finite number. Doesn't really matter that much what it is. A finite number, so infinity minus a constant, and the answer is infinity, right? I think I once saw a cartoon in a math journal. It said, Hotel Infinity, there's always room for one more. Because, infinity plus a constant, we're still getting infinity, etc. Okay, how about the next one? How do we solve that integral? Any suggestions? I could try to apply fancy techniques like trig substitution or maybe partial fractions, things like that, but there is no need, because this one actually works with u sub, right? Let u be, and let that be always your first choice. Try to apply u sub when it's a problem, or a simple formula if there is a formula. If none of these simple techniques apply, then think more complex. In this case, let u be r to the 4 plus 1, right? Then du equals 4r cubed dr. And r cubed dr will be du over 4. So first I will factor out that 8. And for r cubed dr, I'm putting du over 4, pulling the 1/4 outside. And the bottom is now u squared. Right? Simple u sub question. Right? So now we have 2 times the integral of 1 over u squared du. We don't even need to, apply the long power rule, meaning if you already know what is the integral of 1 over u squared. Negative 1 over u, right? So now we have negative 2 over u. Before plugging the limits, bring the original variable back, u being r to the 4 plus 1. And now let's worry about the limits. Okay, first the upper limit of 1. We're getting negative 2 over 2, in other words, negative 1, minus now the lower limit of negative infinity. Okay, as r goes towards negative infinity, what happens to this quotient, negative 2 over r to the 4 plus 1? Negative infinity raised to an even power, what will happen to it? Think of negative infinity as something like, let's say, negative 10 billion, something like that. Just to see the patterns emerging. if you raise it to an even power, it's going to turn into a very large positive number, right? You're adding a constant that's still going towards infinity on the bottom. And so you're taking a ratio now, a constant on the top over something that goes to infinity on the bottom. So the ratio goes towards where? 0. So now we have 0 from the second part. So the answer turns out to be -1. Okay, another example. This one should help you with one of your group activity questions. Any questions about the solution before we try another one with improper integrals? Okay, so the question is integrating from -infinity to 2 of, it is from -infinity to -2 of 2 over x squared minus 1 dx. As always, let's not be intimidated with these infinite limits of integration. Let's just concentrate on the problem itself, the anti-differentiation problem. What technique could we use there? U sub is not going to work, right? There is no x dx on the top. What else could we try? I heard trig sub and I heard partial fractions. Chances are both of those methods could be used here. But I think partial fractions is going to be easier. Partial fractions will be easier. Exactly. We can begin by factoring it as x minus 1 times x plus 1. So this problem can be written as a constant a over x minus 1 plus another constant b over x plus 1. Again, we've done many of these kinds of questions in that section when we covered partial fractions. So we get common denominators, so multiply the first top and bottom by x plus 1, and the second top and bottom by x minus 1. And we're setting the numerators of both sides equal, because denominators will already be equal there. Okay, so, and to solve for a and b, what method would you suggest I do here? Let's plug some values for x. In this case, I'm going to use 1 and -1. So did we all get our a's and b's for this question? I got a's 1, b's -1. If you flip them around, in the beginning maybe you have a over x plus 1, b over x minus 1. Your constants will be flipped as well, but it doesn't matter. You'll have two same fractions as I have on the board. Okay, integrating this is very easy, right? That's the whole purpose of partial fractions, so that we end up with something easy to integrate. But now we still have to worry about the limits, which were from -infinity to -2. It's not going to be a problem plugging the upper limit of -2, but when you deal with the bottom limit of -infinity, which will turn into positive infinity in these absolute value signs, you're going to end up with something of the form infinity minus infinity, and that is indeterminate form. Is there any way we could try to simplify it before we try to plug in our values? Yes, Joshua?
We should put the x minus 1 over x plus 1, because that's one of the properties of logarithm.
Okay, so let's use the property of log, and if you have ln a minus ln b, it's going to be ln a over b, exactly. So we're going to have ln of x minus 1 over x plus 1. At least now we got rid of the infinity minus infinity type of a situation, and it should work out a little bit easier now. Okay. You always wonder, why do we have an absolute value sign when we integrate a ln function? So it really comes into play when you have limits of integration, and especially a negative value. Um, but I think even in this case, you have negative over negative, it still turns out to be positive anyway. But in case you end up with a negative value within an ln function, the absolute value ensures that it's going to be well defined there. So let's plug in negative x, rather negative 2 for x. Okay, what will happen? So I'm getting ln of 3 there. What will happen now if I substitute negative infinity for x on the top and the bottom here? Basically, I have something like of the form negative infinity over negative infinity. So which is another form of Lhopitals rule, because the negatives, you can always take it outside, factor it outside. So you have like infinity over infinity in a sense. You can either use the rule you learned from Calc 1 to quickly find that limit, or use Lhopitals rule. Do we remember if you have infinity over infinity, how do you find the limit of this inner part, x minus 1 over x plus 1? What is the limit of, first of all, just the inner part? 1, right? Degree of the top equals to the degree of the bottom. Take the ratio of leading coefficients. Suppose you forgot that rule from Calc 1. Now you have infinity over infinity. You know L'Hopital's rule, right? Differentiate the top part, what do you get? 1. Differentiate the bottom, you get 1. Once again, 1 over 1 is 1. But that is within an ln function. Don't forget that. So now you have ln of 1. Again, this time we dealt with something of the form negative infinity over negative infinity. Basically, L'Hopital's rule applies even when you have like infinity over negative infinity or things like that, because a constant, a negative value, you can always factor it outside of your limit. It really is not going to change the expression that much. So you can still use L'Hopital's rule when you have slight variations of infinity over infinity with another constant in there. So what is our final answer then? ln 1 is 0, right? So what is our answer? ln of 3. Yes. Okay, one more example on improper integrals. Once again, I'm going to give you a little bit of time to think about it. So if you're watching it online, please pause your video. If you're in class, just take a few moments. If my dv is e to the negative x dx, what would v be? Exactly, negative e to the negative x. Technically, you're dividing by -1 when you anti-differentiate, when you integrate, but that just shows up as a coefficient of -1. Okay, so the rule tells us the u times v minus integral of v du. Minus integral of v du. V brings another negative. Simplifying that quantity, has plus the integral of e to the negative x dx, and integrating it once again. At this point, you know whether or not you've used the right technique, because if this becomes more difficult integral than you started with, chances are you picked the wrong u and dv. Go back and maybe switch them around. This should be easier than the original problem, and indeed it is, right? So we have negative x e to the minus x, and the integral of e to the negative x, once again, is negative e to the negative x. And now we're going to worry about the limits. But before I bring them in, I'm going to go ahead and factor out e to the negative x. And the limits are from 0 to infinity. When you're dealing with infinity and with negative exponents, I find it much easier if you can drop the negative exponent, the expressions with negative exponents into the denominator. Um, that way, it's just easier to see the results. So that's what I'm going to do. I'm going to rewrite this as negative x minus 1 divided by what? E to the positive x, right? Going from 0 to infinity. Okay. Once again, when the limit is infinite, we're literally taking a limit as x goes towards infinity. In this case, we're going to have the top is going towards negative infinity, the bottom is going towards infinity. It's one of those versions of infinity over infinity, basically. How can we resolve that limit? Or do you actually see by looking at it what's going to happen there? Basically, the exponential function grows much faster than the regular x function. The bottom is going to infinity much faster than the top, and the ratio is going to go towards 0. But now let's explain it with the Lhopitals rule. Okay, so if you have infinity over infinity or negative infinity over infinity, you would differentiate the top and the bottom separately, right? Differentiate the top, and what do you get? Negative 1. Differentiate the bottom, you still have e to the x. Now, where does this go as x goes towards infinity? A constant over infinity, and that will go towards 0. So, minus, now let's plug in 0 for x. And e to the 0 is 1. So we're getting negative of negative 1 over 1, or positive 1 once again. Okay, finally, I'm going to give you a couple of examples. These are going to be pretty short ones, but they're a little bit unusual. Maybe they are still called improper integrals, but something that we haven't yet seen before. They're a little bit different. There we go. For instance, integrating 1 over x cubed from 0 to 2. This is a different type of improper integral question. Integrating 1 over x cubed from 0 to 2. Okay, first thing you might say is, wait a minute. You know, I don't see an infinite limit here. How come this is an improper integral? There is no limit of infinity involved, right? But take a look at what happens at x equals 0. The function is undefined at 0, right? So when this happens, when you're integrating something over a point of discontinuity, that is also called an improper integral, a different type of improper integral. And you first, guess might be, well, we cannot do this kind of an integral. Actually, there is a way to do it. And the technique basically relies on the following. Let's say you have a function that is not defined at 0. Maybe the function looks something like this. And let's say you're integrating the function from 0 to 2. Okay. Instead of integrating from 0 to 2, what we can do is the following. We can put a finite limit there, such as, call it any value you like. I'm going to call it t. So instead of going from 0 to 2, we're going to integrate from the value of t to the value of 2. And guess what we're going to let t approach? If you're let t approach towards 0 from the right or from the left? Let t approach to 0 from the right-hand side, correct? So basically, if the original question, if this was my f of x, and if I want to find the integral of f of x from 0 to 2, and it's not defined at 0, right? So the trick is the following. What you do is you integrate it from t to the number 2, but then you take a limit. You take a limit as t goes to where once again? T goes to 0, in this case from the right-hand side. You can do a similar trick if you're going from like negative 2 to 0 this time. T would approach to 0 from the left-hand side. If your discontinuity was something like this, if this was your function, and you want to integrate, let's say, from negative 2 to 0, once again, put a finite t in there at the moment, and let t approach to 0 from the left-hand side. So like in this case, from 0 to 2 of 1 over x cubed dx, once again, ignore the limits. The limit looks weird because it's not continuous there. First integrate. What is the integral of 1 over x cubed? That's integrating x to the minus 3, right? And what is that integral? X to the negative 2 divided by negative 2, correct? In other words, negative 1 over 2x squared, and now we're going to worry about the limits from 0 to 2. The upper limit poses no problem whatsoever. We get negative 1 over 8 out of that, right? Plugging 2 for x. 2 squared is 4. 4 times 2 is 8. Okay. Now here's our problem. When you try to plug in 0, you can't, right? Because it's undefined. So what we should try to do is we should try to take a limit of this quantity as x goes to 0 from which side? We were dividing by negative 2, right? So that's why my 2 is in the denominator. Again, we added 1 to the power and we divided by the same power, right? And we rewrote it. So now try to take basically right now what we're going to try to do is take a limit of this quantity. Again, the interval was from 0 to 2. It's not defined at 0, so we pick a number, a variable such as t. Now we're going to let t approach towards 0. So if you were looking at this as a limit question where we're approaching to 0 from the right-hand side, what do we get? The bottom is getting smaller and smaller and smaller. So we did upper limit minus, now we're doing the lower limit. Remember, that has another negative in it. So what happens to negative 1 over 2x squared as x approaches towards 0? Basically, it becomes negative infinity, right? Because the negative 1/2 was already there. Just keep it aside. What happens to 1 over x squared? X is getting smaller and smaller. The ratio is getting larger and larger, right? So there we have infinity. So it looks like we have a weird situation, like an 8 and an upside down 8, right? But what it is you have a constant plus infinity. So what is the end result then? Infinity. So we can deal with situations where you are integrating over a point of discontinuity. You just have to be really, really careful. And usually we handle those as a limit question. For example, there's a problem in your homework. I believe it was number 11 because I checked before I came here. And they're asking you a question such as, like you're integrating negative 2 to 2 of something like 1 over x squared dx. If you are integrating over a point of discontinuity, what is the point of discontinuity for this function? Where is 1 over x squared not defined?
0.
When x equals 0, right? So technically, you know what we should do for this? We should split into two integrals. Go from negative infinity to 0, and then go from 0, I'm sorry, I said negative infinity. I should have said negative 2 to 0, and then go from 0 to 2. And if only one endpoint is discontinuity, there's a point of discontinuity, you can handle it like we just did over here. If you try to go directly from negative 2 to 2 in this question, you're going to get an absolute wrong answer, and that's what the question was asking you there. It says, why is this answer wrong? And you're supposed to say, it's wrong because you cannot integrate in one shot from negative 2 to 2. You need to go for this question, negative 2 to 0, and then of the same function, 0 to 2. So you have to split it at its point of discontinuity. But sometimes when you deal with points of discontinuity, you get a finite answer. So this is the last example I'm going to show you on improper integrals. Let's integrate from 0 to 1, the integral from 0 to 1 of dx over the square root of 1 minus x squared. At 0, we're fine. The square root is well defined. At 1, the square root is not defined, right? But if one of the endpoints is a point of discontinuity, you can still do the problem Just at the end, think of the limit approach if you need to. First of all, let's integrate. Forget about the limits, as always, right? What is the integral of dx over the square root of 1 minus x squared? Anybody who recognizes that? Arc sine. Very good. Sine inverse of x. And the limits are from 0 to 1. So as it happens in this case, sometimes when you take the antiderivative, that discontinuity in a sense disappears. You don't even have to worry about a limit anymore, because sine inverse of 1 is well defined, right? And sine inverse of 0 is well defined, so nothing to worry about. So in this case, what is sine inverse of 1? At which angle is the sine function equal to 1? Think of the unit circle. Where is sine equal to 1? Sine is 1 up here, correct? Which is pi over 2, and the answer should be in terms of radians. Okay. Minus, what is sine inverse of 0? When is the sine function 0? Right here, right, at 0. So we have a perfectly good answer here, no infinity involved at all. Again, it's kind of surprising, but that's what's happening for the sine inverse function. Even though it was an improper integral, sometimes you will end up with a finite answer like we had here.